Welcome to the Deep Dive, the only shortcut you need to master complex topics quickly. Today, we're not just looking at the network, we're kind of examining its nervous system.
That's a good way to put it.
We are diving deep into these sophisticated protocols that act as the eyes and ears of modern IT infrastructure.
Right.
Network monitoring protocol.
Right. They're the tools ensuring everything's running smoothly, health, performance, and critically, security. All the time.
And our mission today, it's pretty critical, isn't it?
It is. We're aiming to cut through all the jargon, the acronyms SOUP, SNMP, syslog, ICMP, flow monitors, and really give you a solid architectural breakdown.
So by the end, you, the listener, won't just know the names.
Exactly. You'll understand why they exist and how they actually fit together, the big picture.
Okay, so let's dive in. The central challenge for, any network admin. You've got thousands of devices, routers, switches, firewalls. How do you possibly manage all that without just being completely overwhelmed?
That's the million-dollar question.
And the first answer, often, is about checking status, which leads us straight to SNMP.
It does. SNMP,
Oh.
Simple Network Management Protocol. It's essentially main language for these status checks.
Okay.
It works on an application layer using a manager-agent model. You have an agent, a piece of software running on the device itself, the switch, the server, whatever.
Right.
And then you have a manager in your monitoring station. The agent is basically just sitting there listening for the manager to ask, hey, what's going on? What's your status?
So SNMP is fundamentally about polling. The manager asks the questions. What kind of questions is it asking? What's it looking for?
Good question. It's asking about specific things called managed objects. Think of these as variables defining device characteristics, stuff like CPU load, whether a port is up or down, memory usage, maybe even the temperature inside the chassis.
And these objects aren't all the same type?
No, they generally fall into two categories. Scalar objects are single values like, say, the system's uptime since the last reboot. Simple. Then you have tabular objects. These are more complex, like tables. Think of a list showing the status, speed, and errors for all the interfaces on a switch. Multiple related entries.
Okay, that makes sense. But here's something I've always wondered. If you've got devices from Cisco, Juniper, IBM, all different vendors defining their own status objects, how does my manager station know exactly which temperature sensor or port status it's asking about? Seems like chaos.
That's where the brilliance of the object identifier, or OID, comes in. The OID is like a globally unique address for every single measurable piece of data on that device.
Like a GPS coordinate.
Exactly like that. It's a long string of numbers, like 1.3, 0.6, 0.1, 1.1.11, which happens to be the standard OID for system description. It uniquely identifies that object within this big hierarchical tree structure called the Management Information Base, the MIB.
The MIB tree.
Right. And that hierarchical structure is key. It means Cisco can define all its special proprietary objects way down one branch of the tree, and IBM can define theirs down another without any risk of naming collisions. It keeps everything organized globally.
So the MIB is the map. The OID is the specific address on the map.
What about the format of the data itself? How does a manager know if it's getting back a number or text or something else?
That's defined by the SMI, the Structure of Management Information. SMI uses a language, ASN.1 syntax, to specify the data type. There's an integer, an octet string, which is basically text.
Or those special types you mentioned.
Exactly. Like a gauge, which can go up and down, think temperature or CPU load, or a counter, which only ever increases like the number of packets received on an interface. It never goes down unless it resets, usually back to 0. SMI also dictates access rights, read-only or read-write. Can the manager just look, or can it actually change the value?
All right, let's talk about the actual conversation. What commands, what messages does the manager send to the agent?
Well, the most basic is the GET request. Simple. Hey, agent, give me the current value of this specific OID. Straightforward.
Then there's the SET request. This is used if the manager has read-write permission for an object. It tells the agent, change the value of this OID to this new setting, like administratively shutting down a port.
But SNMP isn't just about the manager asking questions, is it? What if something urgent happens on the device?
Good point. That's the trap. A trap is an unsolicited message from the agent to the manager. The agent proactively sends an alert saying, hey, something important just happened, like a port going down unexpectedly or a power supply failing.
So the agent can initiate communication too. Now, you mentioned reading tables earlier. Asking for every single interface status with individual GET requests sounds Slow.
Terribly slow, especially on a big switch with maybe 48 ports or more. That's why we have the GetNext request. Because the MIB is hierarchical and objects are ordered, GetNext basically says, okay, I just got the value for this OID, now give me the value for the next OID in the tree.
So it walks the table.
Precisely. The manager just keeps sending GetNext requests, and the agent responds with the next piece of data in sequence. It lets you read an entire table without needing to know every single specific OID beforehand. Very clever.
And didn't newer versions improve on that even more?
They did. SNMP version 2 brought us the get bulk request. This was a huge efficiency boost. Instead of asking for just one next object, get bulk lets the manager say, give me the next 10 objects, or however many it specifies, all in a single request-response cycle. Massively speeds up retrieving large tables.
Makes sense. But efficiency isn't everything. What about security? Early SNMP had a pretty bad reputation there.
Oh, absolutely terrible. SNMT v1 and v2 relied solely on something called the community string. It was just a plain text password, essentially. The defaults were often public for read-only access and private for read-write.
So basically no real security at all. Anyone sniffing the network could grab the community string.
Exactly. It's like leaving your house key under the doormat with a sign pointing to it. This was a major weakness.
How was that fixed?
SNMP v. Version 3 was a complete overhaul focused squarely on security. It introduced proper authentication using cryptographic hashes like MD5 or SHA to verify the sender's identity. It added privacy, meaning the actual SNMP data gets encrypted using standards like DES, or preferably now, AES.
So no more eavesdropping.
Correct. And critically, SNMP v3 allows for much more granular access control. You can configure it so this user account can only read interface statistics, while that admin account can write configuration changes, but only to specific parts, specific branches of the MIB tree. It's a world of difference.
That's a huge improvement. Okay, so SNMP gives us this powerful way to pull devices for status and make changes securely if we use v3. Now, if SNMP is mostly the manager asking the device questions, what about when the device needs to, well, sort of yell at the manager about something happening right now? You mentioned traps, but is there another way?
There is, and it's a very common one. syslog, the system logger. Think of syslog as an asynchronous protocol. Unlike SNMP, where the manager pulls data, with syslog, the device pushes messages out.
Pushes them where?
To a central syslog server or collector. The device itself could be a router, a server, a firewall, generates log messages or event messages like configuration changed, user login failed, VPN tunnel established, and it just sends them off, typically using UDP port 514 to that central server. The manager can't pull for syslog data, it just listens for these incoming messages.
And the real utility here is how those messages are categorized, right? Otherwise, it's just a flood of noise.
Exactly right. Every standard syslog message has two crucial fields for categorization baked in. First is the facility, which tells you where the message came from on the device. Was it the kernel, the mail system, the routing process, the firewall?
So you know the source?
Yep. And second is the severity level. This is a number from 0 to 7 indicating importance. Level 0 is emergency system unusable. Level 1 is alert, action must be taken immediately, all the way down to level 7, which is debug informational messages.
And these combine somehow.
They do. They combine into a single priority value, often called the PRI. The calculation is simple, facility code 8 plus severity level. The key thing to remember is that a lower final PRI number means a higher actual priority message. This allows the syslog server to instantly filter and flag the critical stuff like seeing a PRI corresponding to an emergency or alert.
That's clever.
Yeah.
But echoes of early SNMP here, UDP 514, sounds like it might have security issues too.
It absolutely does. Standard syslog over UDP has no built-in authentication or encryption. The server just receives messages. It can't easily verify they actually came from the device they claim to be from. Meaning it's vulnerable. An attacker could potentially spoof messages, maybe flood the server with fake critical alerts to distract administrators or inject false information. There are secure versions like syslog over TLS, but basic syslog is inherently insecure.
Okay, good to know. So we've covered polling status with SNMP and receiving pushed alerts with syslog, but both of these kind of assume the device is, well, up and running enough to respond or send messages. What about the most fundamental check? Is this thing even alive on the network? Can I reach it?
Now you're talking about ICMP, the Internet Control Message Protocol. ICMP is really the bedrock of network diagnostics and error reporting.
And the tool everyone uses based on ICMP is?
Ping. The classic Ping utility uses ICMP echo request and echo reply messages. Your machine sends an echo request to a target IP address. If the target is reachable and allowed to respond, it sends back an echo reply.
Simple but effective.
Very. Ping tells you basic reachability. Is it up? Measures the round-trip time, or RTT, how long did the message take to go there and back. And it can also show you packet loss. Did all my requests get replies? It's absolutely essential for just active up-down monitoring.
But ICMP does more than just ping the final destination, doesn't it? It helps map the path.
It does, through tools like Traceroute or Tracert on Windows. Traceroute cleverly uses packets with increasing time-to-live TTL values. Each router hop along the path decrements the TTL. When TTL hits 0, the router sends back an ICMP time-exceeded message.
Ah, so you collect those messages from each hop.
Exactly. Traceroute sends out probes, gets back these ICMP messages from each router along the path, and uses the source IP of those messages to show you the route, hop by hop, along with the latency to each hop. Traditionally, it used UDP packets for the probes, but many implementations now use ICMP echo requests as well.
And there's even more powerful tool that combines these.
Yes, MTR, which stands for My Traceroute, or Matt's Traceroute, depending on who you ask. MTR basically runs ping and traceroute continuously in one display. It repeatedly sends probes, usually ICMP echo requests, to each hop along the path.
Why is that better?
Because it gives you real-time ongoing statistics for each hop. Latency, jitter, and crucially, packet loss at each specific hop. If you're having connectivity issues to, say, a cloud service, MTR is invaluable because it can pinpoint where along the path the problem is occurring. Is it your local network, your ISP, or further out? And because it often uses ICMP echoes, it can sometimes get through firewalls that block the UDP packets used by traditional traceroute.
Okay, that makes sense. So we have device status, SNMP, alerts, syslog, and connectivity checks, ICMP. But none of these really tell us about the traffic itself. You know, who is talking to whom on the network and what applications are they using, how much bandwidth are they consuming. That feels like a different category.
It absolutely is. This moves us into the realm of flow monitoring, which is about understanding traffic patterns, not just device health.
Where did this start?
Well, one of the earlier efforts was RMON, remote monitoring. RMON was actually an extension of SNMP. It defined specific MIBs for monitoring network traffic, particularly on LAN segments.
So it used SNMP underneath.
Yes. RMON agents, often built into switches or dedicated probes, would collect traffic statistics locally. Packet counts, byte counts, errors, broadcasts, collisions on Ethernet segments. The key idea was local collection and processing to reduce the load on the central SNMP manager. RMON also introduced the concept of collecting historical data and analyzing flows like traffic between two specific MA addresses rather than just instantaneous device counters.
RMON had different versions too.
It did. RMON 1 focused mostly on layer 1 and 2 statistics. RMON 2 added capabilities for higher layers, looking into IP addresses and application protocols. But while important historically, RMON has largely been superseded by more modern flow technologies.
Like NetFlow.
Exactly. NetFlow was originally a proprietary technology developed by Cisco. It became incredibly popular, and the IETF eventually standardized a similar concept as IPFX, which stands for IP Flow Information Export. So today we often talk about NetFlow, IPFX somewhat interchangeably, though there are differences.
Okay, so what is a flow in this context?
A flow is typically defined as a unidirectional sequence of packets that share several common properties. The most common key fields that define a flow are source IP address, destination IP address, source port number, destination port number, layer 3 protocol type like TCP or UDP, class of service marking, and the router or switch interface the packets arrived on.
So all the packets belonging to my web browsing session to a particular site would likely be part of the same flow.
Pretty much, yes. As long as those key fields match, the packets are grouped into the same flow record by the network device.
How does this work in practice? How does the data get from the router or switch to somewhere I can analyze it?
The device that observes the traffic, let's say a router, acts as the exporter. It has a process, the flow cache, where it examines incoming packets. If a packet matches an existing flow in the cache, it updates the statistics for that flow, like byte count, packet count. If it's a new flow, it creates a new entry.
Okay, then what?
Periodically, these flow records need to be sent off for analysis. The exporter bundles them up into data messages and sends them, usually via UDP, to a central flow collector. This collector is basically a server whose job is to receive these records, store them, often in a database, and make them available for analysis tools.
When does a flow get exported? Does it wait until my web session ends?
Good question. Flows are typically exported based on timers. There's an inactive timer. If no packets belonging to a flow are seen for, say, 15 seconds, the flow is considered finished and gets exported. There's also an active timer. Even if a flow is continuously active, like a long file transfer, it will be exported periodically, maybe every 1 or 5 minutes or even 30 minutes, depending on configuration, to provide ongoing visibility.
And what do people do with all this flow data?
All sorts of things. Capacity planning. See which links are getting congested and by what kind of traffic. Traffic analysis. Understand application usage patterns. See who the top talkers are. Security monitoring. Detect anomalies like DDoS attacks, scanning activity, or data exfiltration by looking for unusual flow patterns. It gives you context that SNMP alone can't provide.
It sounds powerful, but also potentially overwhelming. Collecting records for every single flow on a busy network must generate a ton of data, right? And put load on the routers.
It certainly can. That's one of the main reasons another technology, S-Flow, was developed. S-Flow takes a different approach.
How so?
While NetFlow IPFX is about aggregating every single flow and exporting records about those flows, S-Flow is based on statistical sampling.
Sampling? Like it doesn't look at every packet.
Exactly. This S-Flow agent running on the switch or router is configured with a sampling rate maybe 1 in 100 or 1 in 1,000 or even 1 in 10,000 packets. When a packet is selected by the sampler, the agent takes a packet sample, typically just the packet header, not the whole payload, and sends it directly to the S-Flow collector.
Just the header?
Usually, yes, along with some metadata. It also periodically sends countersamples, which are snapshots of interface counters, much like you'd get from SNMP, but pushed out proactively.
So S-Flow is sending raw sample packet headers and interface counters, while NetFlow IPFX is sending summarized records about completed or active flows.
That's the core difference. S-Flow sampling means it generates significantly less data than NetFlow IPFX, especially on very high-speed links. It also puts less processing load on the network device because it's not maintaining a big table of active flows. This makes FastFlow extremely scalable. The trade-off is that you're getting a statistical view, not a 100% complete record of every single flow.
Different tools for different needs then. NetFlow IPFX for detailed accounting, S-Flow for high-scale visibility.
That's a good way to summarize it. Okay, we've covered a lot of ground. SNMP, Syslog, ICMP, ARM-ON, NetFlow, IPFX, S-Flow. But there feels like one crucial underlying piece we haven't talked about. Imagine this. Your firewall sends a Syslog alert about a potential breach at, say, 2:00 p.m. exactly. Then, 5 minutes later, the server involved sends its own alert related to the same event, but its clock says 2:00 p.m. because it's 5 minutes fast. How on earth do you correlate those events accurately?
You've hit on an absolutely critical foundational requirement, time synchronization. And the protocol for that is NTP, the Network Time Protocol.
Why is it so vital?
Because without accurate synchronized clocks across all your devices, correlating events becomes a nightmare, if not impossible. Think about troubleshooting, trying to piece together a sequence of events from logs on different systems, or security analysis proving when something happened based on timestamps from multiple sources. If the clocks are off, your whole timeline is wrong. NTP's job is to keep all those clocks aligned, usually to Coordinated Universal Time, UTC.
And NTP isn't just a free-for-all. Is there some kind of structure to how devices get the time?
There is. NTP uses a hierarchical system based on stratum levels to define the accuracy and trustworthiness of time sources.
Stratum levels. How does that work?
At the top, you have stratum 0. These are the ultimate reference clocks, things like atomic clocks, cesium, or GPS receivers. They're the most accurate sources, but you don't typically sync directly to them over the network.
Okay. So where do network devices sync?
They sync to stratum 1 servers. These are computers directly connected to a stratum 0 reference clock. They are highly accurate time sources available on the network. Then, servers or devices that sync their time from a stratum 1 server become stratum 2. Devices syncing from stratum 2 become stratum 3, and so on.
So the stratum number indicates distance from the primary reference clock.
Exactly. Each hop away increases the stratum number. The hierarchy goes from stratum 1 down to stratum 15. These are all considered valid synchronized time sources, although accuracy generally decreases slightly with higher stratum numbers.
What happens after 15?
Stratum 16 is special. If a device reports stratum 16, it means it's unsynchronized. It hasn't been able to reach a valid time source, so its time should not be trusted. NTP is really the unsung hero that makes reliable logging and event correlation possible.
Wow. Okay, this has been a really comprehensive deep dive. Let's try and pull it all together for the listener. A quick summary of the roles.
Sure. So we've seen that SNMP is primarily for polling device status and configuration details, querying MIBs. Syslog is for receiving asynchronous, real-time event alerts pushed from devices. ICMP provides essential reachability testing and path diagnostics using tools like ping and traceroute.
And the flow protocols.
Right. NetFlow IPFX gives you detailed records about traffic flows for accounting and analysis, while SFlow offers a scalable, sampling-based approach for high-level traffic visibility. And underpinning all the timestamping is NTP, ensuring everyone agrees on what time it is.
So you really need a combination of these for effective monitoring, don't you? They aren't competing. They're complementary pieces of the puzzle.
Absolutely. You need to know if a device is up, ICMP, what its health metrics are, SNMP. Be alerted if something bad happens, Syslog SNMP traps. Understand the traffic patterns, NetFlow's flow, and have it all accurately timestamped, NTP.
You, the listener, should now have a much clearer picture of how these protocols map the data on your network, using MIBs and OIDs via SNMP, how they map time using NTP and Syslog timestamps, and how they map traffic flows using IPFX or SFlow. But maybe let's leave you with a final provocative thought, especially thinking about security. Where does the real power in network monitoring actually lie today?
That's a fascinating question to ponder. Is the true power still with the central manager, having the ability to constantly poll every device, asking, are you okay? What's your status? That kind of traditional centralized command and control approach we see with SNMP GET requests. Or is the power shifting? Is it more about the device's own intelligence and its ability to autonomously recognize a critical issue and instantly alert you yelling for help via an SNMP trap or a high-priority syslog message without waiting to be asked?
Control versus notification speed. Centralized polling versus distributed alerting. That's definitely something to think about when designing or optimizing your monitoring strategy. Which model gives you the security edge you need?
Worth considering.
Indeed. Thank you for joining us for this deep dive into the world of network monitoring protocols. We'll catch you next time on The Deep Dive.